Hello everyone, this is Ivan and I am glad to see you again. Today I would like to talk with you about errors and mostly we will be focused on error transformation from polar reference frame to Cartesian one. There are many different sensors that can provide us only range and some angular data. And uh, next, after the measuring, we have a task of data transformation from polar reference frame to the Cartesian one, because in most cases we need x and y data, and this metrical data are very welcome for different mathematical methods application, for filtering, for data processing, for trajectory detection, and for any other applications. Um, of course, one of the most useful sphere of these sensors it is the radars in civil or military aviation, because each primary or secondary surveillance radar give us two main coordinates. It is range for object or for meteorological object and angular data. In most cases, in such sensors, angular data is measured from a direction to the north. That's why it uses hidden angle for uh, measuring and representation of object coordinates. Also, some other sensors can perform object localization in three-dimensional space. And in this case, of course, we've got one range and two angles. First one will be in horizontal plane, it can be hidden angle, and other one will be in vertical plane, which usually called elevation angle of object. Thus, two angles and one range will identify any object in three-dimensional space. However, today I will be also most focused on only two-dimensional space, and we will consider case of having input data as range and hidden angle. Also, some sensors can use their own reference frame, and in this case it can be body reference frame, and angular data can be counted from the center line of our sensor. Let's start to talk about it. First of all, let me introduce a little bit of theory. If we have true location of our object and we've got some sensor that can measure location of this object, if it will be ideal sensor without any errors, we will get rho and theta angle. In my case, I use as radar an example, and in this case I directed x-axis to the north, which is associated with the center line of this radar, and y-axis will be directed to the east. And angle theta, it will be angular coordinate of my measured object, and in this case of reference frame orientation theta, it will be hidden angle of of my object in space. And that's why we've got theta and rho, two of these coordinates, identify object location in horizontal plane. However, during the measuring process, some random factors can influence, and finally we've got errors of measuring. And due to measuring two parameters, range and angle, we've got two different errors influence. First error influence in range measuring, and in my case it will be represented as an additive value eta rho. Yeah, this one. And in angular measuring, this error, it will be eta theta. Finally, after the measuring, these errors will be added to the true location, and we've got measured location of our object. And let it be located somewhere here where I marked as a red star. That's why usually when we apply multiple time measuring process, we will get multiple stars located over the true location. And due to normal influence of normal error influence into measuring process, the most measurements will be distributed by Gaussian probability density function. And basically today I would like to tell you how errors from polar reference frame will be transformed to the errors of Cartesian reference frame. If we can draw Cartesian reference frame, and for simplification, this reference frame will be located in the reference point of sensor location. In this case, true location will have coordinates x and y, and measured location got x and y coordinates, however, with a star. And error of measuring, it will be eta x. This one, it will be error of measurements by x coordinate, and eta y, which will be error of measuring in y direction. If we apply transformation from polar to Cartesian reference frame, in this case of axis orientation, we will get that x measured will equal rho measured multiplied with a cosine of theta measured. Also, y measured is equal rho measured multiplied with the sine measured theta angle. This is like polar to Cartesian transformation equations. However, if you would like to understand how errors will migrate from one reference frame to another one, we need to consider only errors. And in this case, I would like to propose you to use Taylor series expansion by first order of derivatives, because you know that Taylor series includes multiple derivatives, and it will be quite long mass formula. If you limit it only for first derivatives, it will be more welcome for computation and will be understandable for everyone. That's why if you consider first x coordinate, we can represent measured x coordinate, which is x with a star here, will be equal function which depend rho and theta from x, and this function represents like true position of this object. Thus, errors of measuring can be represented as the following addition coefficient in this Taylor series expansion equation. And in this case, first derivatives of this function by first parameter rho, we need to multiply with a difference by rho. It means we need to multiply measured value from true value, and plus the same for next parameter. In this case, it will be first derivatives by this function by theta parameter multiply with difference between measured and true theta angles. Otherwise, we can represent it as true value x, which we do not know, will be plus derivatives by rho multiply with eta rho. Eta rho in my graph, it is measured error of distance measuring, plus first derivatives by theta multiply with eta theta. And in the more welcome form, we can represent it as an x plus error by x. In this case, all of that, it is a value of error by x. That's why we can represent that eta x is equal to this sum of first derivatives by different parameters. If we can rewrite it, and then let's try to find first derivatives by parameters. If we consider x axis, it means that first of all we need to find first derivatives from x relation, and in this case first derivatives from rho cosine theta by rho. It will be just cosine theta, because first derivatives from rho by rho, it will be 1. 1 multiplied with the cosine theta will be cosine theta. That's why here we've got cosine theta. Multiply with eta rho minus, why we've got minus? Because first derivatives by cosine, it will be minus sine. That's why rho will still rho minus rho multiply with sine of theta. And of course, we need to multiply with eta theta, which is immediate error of theta angle measuring. Usually errors we represent as mean square deviation error. However, mean square deviation error, it may be not very useful. That's why usually we talk about dispersion. And dispersion, it is a squared value of mean square deviation. That's why dispersion, it is sigma x squared. And dispersion, usually we can represent as a mean value by multiple measurements of x error squared. That's why mean value from squared errors will be equal to mean values from squared value of this equation. If you remember from arithmetic operation, then we can open the brackets and we will get squared values for this one minus double multiplication of both components plus squared value of the last element, which I've got here. Yep. Due to usage absolutely different measuring sensors, which has different errors, which is not correlated. It means that eta rho and eta theta, these errors are absolutely different. Yes, and this is true because first one it is ranges and errors of ranges, and the second one it is errors of angles, which is different units of measuring. And correlation between them is equal to 0, and that's why mean value from multiplication between two of these errors will give us 0. And it means that this middle part will be equal to 0. That's why we can left only first part and the final part. And in this case, we can rewrite everything in more common way. In this case, we can change mean value for eta rho squared to the mean squared to dispersion by rho, and mean value from eta squared theta to dispersion by theta angle. That's why we've got quite a simple formula for analytical estimation of errors by x-axis if we know sigma rho, or dispersion by range measuring equipment, and dispersion by angle measuring equipment. The same we can do for y coordinate. To do that, we just need to apply the next equation for coordinate transformation. That's why we can write y. Y value is equal to the same. However, next we will add y, and here we've got the same unless sine and cosine, because in this case first derivatives by rho from sine, it will be sine theta, that's why we still sine here, plus first derivatives from sine by theta, by angle, it will be plus cosine, that's why it will be plus rho cosine theta. And then if we continue at the same way, we've got approximately the same formula. However, sine and cosine will change place between each other. That's why two of these formulas, usually called analytical formulas for error transformation from polar coordinates to the Cartesian one. And usually these equations are used in data processing of radars in civil aviation in order to understood the area of uncertainty related to each object. Okay, if there is no questions for you, however, I will be glad if someone in the comment related to this video give me formulas to estimate sigma z. If you got third angle elevation, that's why we can find projection of z to the horizontal plane, and then we can apply the same formulas. However, we will have additional for z. That's why if someone would like to try it by yourself, I will be glad to assist you. That's why just take a whiteboard, then write your formula for z-axis, and taking into account elevation angle, and then represent me sigma z, and I will check if you're correct. Actually, now I would like to show you how these errors will be in practice if you talk about civil aviation radars. And of course, we will try to approve these formulas with the help of statistical modeling in Matlab. That's why now I would like to switch on my Matlab, and we will continue mathematical simulation of these formulas in Matlab. Just a second. Yep, I've got it. This is my Matlab environment, and also I would like to open my script editor, and as usual I will start my code in Matlab from 3 lines of description, what we will do next, and next of course I will add 3 lines which is help us to prepare a workspace of Matlab for all further computation. That's why it will be CLC clear all just a second clear vars we use, and close all. These 3 lines prepare our Matlab environment for further computation. Then let's try to evaluate dependence of this transformation from different theta and rho, because as you see that sigma x and sigma y are in relation from angle theta and rho. That's why this is not like usual errors. It will be related from object location in space. That's why first of all let's specify range of angles theta which we would like to estimate. That's why we specify matrix theta, and I will evaluate from 0 degree with a step 1 to 359. And it means that we will try to approve this formula for each direction in our circle. And also I will put a description that this theta angle will be in degrees. Then I will use 3 different, okay, maybe not 3, 4 different ranges. That's why I will specify matrix R, and I will specify 30, 90, 120, 300. 100. And these values, it will be matrix of ranges. And these ranges will be in kilometers. Due to further computation, I like to get everything uh, in C scale. That's why I will use transformation from kilometers to meters. That's why R will be equal to R multiplied with 1e3. That's why we transform to meters. Then, if you talk about measuring, we need to specify mean square deviation of measuring. If you talk about civil aviation radars, usually angle measuring um device usually has accuracy between uh, zero point 0.1 up to 0.5 degrees. That's why I will specify sigma theta as 0.5 degree. So degree. And then we will specify uh, mean square deviation of range measuring, which in most cases depends on distance to the object. It means that objects located more close to radar will be detected more precisely than objects located so far. And in this case, I will specify that sigma r will be 1/10,000th of measured range. In the normal case, it means that sigma r for 30 kilometers will be 3 meters. For 90 kilometers, it will be 9 kilometers. For 120, it will be 12 kilometers. And for 300 kilometers, it will be just 30 meters. However, always we can play with this data to get more accurate data than we would like. Then let's try to type these two formulas to estimate sigma x and sigma y and plot it in our graphs for different ranges. To do that, let's use a loop for changing different ranges. That's why in loop we will run two formulas for getting different sigmas for different ranges for all angles theta. That's why I use 4 with the loop variable I, which is equal from 1 to number of elements in matrix R. If you use 4, that's why we need to specify and, then we will put formula for sigma x. However, in this case, I will use matrix form, and I will specify it in the following format. In this case, all theta angles will be accumulated in different columns. However, lines or rows will be connected with ranges. That's why in the result I will have matrix with 4 rows and 360 columns. That's why I just specified something like that, and then I will try to quote this equation. That's why I will use function power to get squared value. That's why power from s dash r of is element, and I use second power. Then I will multiply it with power of cosine. Uh, just a second. Cosine d from matrix theta. From matrix theta, and also I use second power level. And then I can use plus. Then I will need to specify row. That's why it will be power uh, r is par. I will use the second power. Then I will need to multiply it with the power s theta as theta. Also I will use second one, and also I will multiply with power of sine d from matrix theta. Theta, the second one. Also quite important here, you will see that in these formulas we've got a dispersion for theta. It is this one. And in our case, we've got mean square deviation, which is s theta in my case. And I will put s theta here. However, we use s theta in degrees. And based on these formulas, we need to put sigma theta in radians, because it does not any sense to multiply degrees with the meters. That's why it is meters multiplied with degrees. It will be it will not be meters. That's why sigma rho in meters, and this one it cannot be in degrees, because it will be meters in degrees, and meters in degrees we cannot add to meters. That's why here sigma theta should be in radians. That's why let's transform it, and we've got function degrees to radians, deg to rad, which we use for s theta transformation to radians. Then I don't want to retype it. I just copy this line and paste and do the same for sy. That's why sy is equal the same. I just need to change cosine to sine, and cosine and sine to cosine. Yep, and we've got our coded formulas. Next, let's find radial value, which will be like square, which will be sum of squared values. That's why it will be SR, which is equal QRT from SX plus SY. Then also, due to, you see that here we got dispersion and here dispersion. That's why it is values in power of 2. That's why I just would like to find square of these values. And I will use sxy variable, and it will be sqrt from x, and as y1 it will be sqrt from sy, and I will close the line. We've got it, and next we can run. Just a second. Yep. And let's check our Matlab environment. And you will see that I do not have any mistakes. I've got my matrices. Everything looks cool. It means that we can try to plot a graph. Only I forget to put semicolon here. And let's play a graph for representation of Sx and Sy. That's why I will create a new section of my code by using to percentage. Then I will use a new figure. It will be figure, and as you remember, we use color properties, property of figure, to specify that it should be white. However, white it should be lowercase, and then we specify name, and also it is a property, and then we specify title for our figure, and let it be analytical errors distribution in the north direction. That's why here we will plot everything related to the fx, and I will use just plot as usual for simple data. Theta, by x-axis we use angle theta, and by y-axis it will be xy, and we will use the first row of this matrix. That's why first one and for all columns. Also let's specify color scheme. I will use probably dashed line and red color to plot this graph, and then I just would like to copy the same to put it for the second range. Yeah, and I will use probably dash dotted green line, and then I will use it for the third one. Sorry, S6 for the third one, and let it be just solid blue. And the final fourth one, it will be false here, and solid magenta line. This comma we do not need. Okay, then let's specify title. I will use the same title as we use in figure capture. Then also it is good behavior to specify axis. That's why x label we use. In this case, it will be theta angle. To specify, I use quad for theta, which is just theta, and we need to specify also that it is in degree. Y label. By Y label, I will use S, which is sigma. That's why sigma, we also have a sigma code, and dash x. It means lowercase for x value. Next, let's specify legend. And here we specify 30 kilometers. Then second, let me check. 90 kilometers. Okay, 90 kilometers. Then 120 kilometers, and then 300 kilometers. Yep, and of course grid on, because grid on makes everything more visible. However, also quite important that usually Matlab tune zoom for x-axis not precisely. This is due to applying like a scale in x-axis. That's why much more better will be to specify x limit to specify limits value for x-axis. And to do that, we can use xlim function, which requires to specify minimum and maximum values for our axis. That's why we use min for minimum value for theta and maximum value for theta. Yep, that's all. And then I just would like to run it. I will use Control Enter to run only this section. Okay, I've got results, and what we have here. That's why we've got distribution. Okay, just a second. I see that I have many mistakes. And first of all, that it should to be not theta, it should to be theta. I forget h. And also sigma x will be in meters. That's why we can specify meters and theta in degrees. And let it be resimulated. Okay, and now it looks much more better. What we can see is that errors of sigma x will be different from theta, and we will see the following forms. Yeah, and also the maximum value of this error will be different based on distance to the object. That's why for the first one it will be quite small. However, later it will be more and more valuable values. And if you talk about 300 kilometers, for our input data, we've got errors at the maximum one as approximately 2,500 kilometers. Let's plot the same graph, however, for sigma x and for total sigma radial values. Therefore, I just would like to copy these lines, put it next. For then I will change title distribution into the east direction, because in this case y-axis in my case directed to the east, and I just need to check sigma x to sigma y. Yep, and here y label to sigma y, and that's all. We will have figure that we need. Next, I will put the same and put it again. Analytical radial error distribution. Okay, I will change the title a little bit. The same for the next title, usage, and I just change it to SR because radial or sigma radial, it is SR variable in my case. And also here are, and let it be resimulated one more time from beginning. And I've got 3 graphs. And we will see how errors will be distributed for sigma x by theta angle, for sigma y by angle theta, and radial one. Okay, we can see that it's quite valuable. However, please take attention that we change because we use different sigma rho for different ranges, and this changes is significant because for the final one it is 30 meters sigma, uh, which is quite that is quite big for for the value. That's why here we've got so big values like 3 kilometers. Okay, let's go next. Next, I would like to verify my graphs because we've got formulas and I would like to check if this formula is true. We've got some graphs, however, we do not know if these graphs are true. That's why we need to approve these graphs and these formulas by other approach. And in this case, statistical modeling by Monte Carlo method will be very, very welcome. To do that, okay, I will need to come back to our code and I will go next and probably I will add new section in my code which will be statistical modeling. And first of all, let's specify how many times we will measure our errors. That's why it will be volume or size of our sample. And for beginning, we can use like 100 measurements for each angle and for each range. Okay, next I will apply 2 loops, which will be more understandable for everyone. First loop will change ranges, the second one change angle or hidden angle. And in each direction and each range we will get n time of measurements, and then we process this statistical data to obtain distribution of sigma x and sigma y based on theta distribution. That's why let's use one loop for with variable I for range, nominal number of elements in matrix R, and the second loop will just a second. I don't want to use the plus, and the second loop will use number of elements in theta matrix. In my case, yeah, it is just theta. And also, if you use loop, means that we should put 2 n's. Yep, and we will continue. Okay, next let's simulate measurements and measurements of theta and measurements of rho. Therefore, I will use theta. I will add just m, which means measured theta. And for simulate measuring process, I will just use random generated function norm R&D, which requires to simulate mean value and mean square deviation for this value. And due to we've got some true value, I will use true value as a mean value. That's why theta. However, theta will be changed with the help of yod variable or loop variable. That's why I will use something like that. And then we need to specify sigma theta. And then function norm R&D generates for us also matrix. That's why we need to specify the size of this matrix. And in our case, it will be 1 row and n columns. That's why this one helps us to get simulated measurements of theta angle for different theta angle. And then let's simulate distance. Also will be rho measured, which is equal norm R&D function with r. However, in this case we use I loop variable because I is connected with r. Okay, this is the first loop. And then we specify sigma rho mean square deviation for rho by I. Yeah, and then specify the same size. Okay, we've got simulation of measured value. Next, we need to estimate. We need to estimate x and y for measured values. That's why we transform from polar to Cartesian reference frame theta and rho data. To do that, I just specify xn. I do not want to use a built-in function of polar to cart, which transform from polar to Cartesian reference frame. That's why I just use the formulas for transformation theta m and yn is equal ym ORM multiply with the sine in degrees, that's why sine d, from theta measured. That's why by these formulas we can easily transform. One more time, these formulas we've got somewhere here. Where it is? Oh, okay. Let me check if I correctly add it. That's why x is equal rho multiplied with the cosine theta, and y is equal rho multiplied with the sine theta. Yes, everything is correct. And also to find difference between measured and true value, we need just to get true value. That's why I just specify true value. Okay, just copy paste it and change it to the x. X is equal r from I multiply with cosine d from theta yod. And y is equal r from I is equal sine from theta yod. Yep, that's why we've got measured value and true value. Next, we need to find a difference between them. That's why I will use sigma x. Okay, it will be measured. Also, I will specify is and yours in the same way as in previous for analytical formulas. And here I will find difference between measured and true value. However, here we've got matrices because we simulate n variables. That's why in this case we need to find standard deviations. That's why it will be STD, mean standard deviation in this resulted matrix. And also the same let's do for y, as y measured or simulated will be I from your equal std from y measured minus y. Okay, and close this line. Okay, it looks well. However, in this small part of code, we will have some variables that will be recalculated multiple times. Because this code will be calculated multiple times. That's why we need to make clear these variables before each computation time. That's why I will add function clear and then specify theta m, then r m, then x m, y m, x and y. That's why it gives me a possibility to make sure that is nothing change in our learning sample. Also, I like also make Ctrl A and then press this button to make smart ident to align all the data in more like nature representation of code. And finally, in the same way, let's count radial, where it will be measured radial, and it will be sqrt from power sx measured by 2 plus power sy measured by 2. Okay, everything is ready. However, before calculation, let's create plotting. In this case, I just copy everything that we've got before and put it at the end and change analytical to statistical. Statistical. Because all other data will be the same. Just a second. And then I will change sx1 to the sx dash measured. X measured, x measured, y measured, y measured, y measured, y measured, and sr measured, r measured, measured, measured. And let's calculate everything. Okay, I left somewhere 360. I don't know from where it's come. And I've got all the results. Just a second. Okay, probably I've got some mistake somewhere. Just a second. We need to check. Okay, I do not have any errors. However, I do not have. Okay. I forgot about Xlim. Oh, everything is correct. Where are graphs? Okay, let me check what's going on. As x measured. Let's check as x measured. Okay. Okay. However, it should be squared matrix. Just a second. Let me check. Okay. I forget here just semicolon. Let it resimulate it one more time. Okay. And I've got data which I would like to show you. And I will try to put everything in one screen. Just a second, in order to compare results. Okay. Okay, one more time. Let me introduce it. First of all, we have tried to use analytical formulas, which we just type, and I hope it was clear for you to understand how it was get it. And we will got the following analytical dependencies of sigma x, or mean square deviation, by x and axis and by y axis from an angle theta distribution. And we see that identical results we've got from statistical simulation, because in this case we simulate 200 measurements for each point and each range. And then we found standard deviation for deviations between two of these points. And we've got the following results. If we can compare radial value, total value, we will see that we've got approximately identical results, unless here we've got noise. If we would like to reduce noise, of course, we need to increase number of computation. That's why if we use, for example, 2000 or even 10,000, we will simulate and plot graphs. you will see that our errors became lower and the amplitude of fluctuation becomes less. That's why statistical modeling are useful. However, in this case, we need to use more computation performance because we need to increase number of uh, input data or learning size uh, or size of learning sample. Okay. Okay. Probably that's all that I would like to tell you today. First of all, please remember that uh, if we have sensor that measure angles, it means that this sensor introduce this quite valuable errors. Any angular sensors is not very well. And you can see that later, if you got a system of distance and angle measurements in navigation, after the transformation from polar to Cartesian reference frame, we will get okay, angular dependent results, and these results will have like zero errors, only in particular like two places, uh, approximately in 90 degrees and in 270. However, it depends on if you talk about sigma x or about sigma y, because it is sine or cosine or trigonometric function. Radial or total error will be different, and you will see that it will have the following results based on our input. However, I would like to tell you that we use quite valuable values, which means that for 30 kilometers we got 3 meters. And just a second, what kind of mean squared deviation we used for angle? It was okay, 0.5 half degrees. Uh, it means for modern radars, it means like the most hard value, because usually it is zero point 0.1 or even less than 0.1. Uh, let try to resimulate for this input value for 0.1. Just a second. My computer will not have very good performance, and in this case, yeah, we've got more correct results which we can associate with modern radars. Just a second. I will show you all the graphs. That's why in this case our radial error becomes like 50 meters or 30 kilometers, then a little bit more than 150 meters for 90 kilometers, and a little bit more than 200 meters for 120 kilometers, and for 300 kilometers range we've got approximately 520 meters. That is not bad for modern civil aviation radars technology. Probably that's all for today that I would like to tell you. Thank you very much for watching me. If you got any questions, always I'm welcome to. I will be welcome for any questions. Of course, smart questions, and I will be glad to answer on it. Thank you very much. See you again, and solving some navigation problems with the help of computer technology. Good luck.